As a first problem for the dynamics of circular motion, let's take a look at this one. A crate of eggs is located in the middle of the flatbed of a pickup truck as the truck negotiates a curve in the road. The curve may be regarded as the arc of a circle of radius 35.3 meters. If the coefficient of static friction between the crate and the truck is 0.60, what is the maximum speed of the truck if the crate is not to slide? So it may help to have a sketch of this situation. So here's the situation. We have the truck here with the crate of eggs in the back. It's traveling around this circle at some constant speed. It may be a little ridiculous to talk about a precision of measuring to the crate of eggs of 1/10 of a meter. That's only 10 centimeters, which isn't much. That's the radius of curvature of the path that the truck is following. And if the eggs are to travel in that curved path, where they will have a centripetal acceleration toward the center of the circle, it's going to take a force, a centripetal force, that points toward the center of the circle, and that will be the friction between the bottom of the crate of eggs and the top of the bed of the pickup. So we'll have that situation going on. So there's our picture. I'm going to make a free body diagram first, and I'll make it from the viewpoint of maybe the back of the truck looking toward the crate of eggs, and I'll just draw the crate of eggs as a dot, as we usually do on our free body diagrams. For the crate of eggs, downward force is going to be its weight. There will be an upward normal force provided by the bed of the pickup. So we have that. And then I'm going to imagine that the center of curvature of the path that it's traveling is to the left here. So that's as good a thing as any, and I'm going to call this F sub S for the static frictional force pointing in that direction. So there's my free body diagram. I'm going to want to apply Newton's second law in a vector form here. So just as a reminder, this is what it looks like. Sum of the forces equals ma, and the acceleration is toward the center of the circle. Sometimes on these circular motion problems, I like to just sketch the direction of the acceleration near the free body diagram. I'm not attaching it to the dot. This is not a force. It's just the result of the forces. It's to the left. Now, I've got my Newton's second law here. The next thing I'll do is write it in terms of this particular problem. The three forces acting, the normal force plus mg plus the frictional force, are going to equal ma. And so I have that. Okay, with problems like this, it's got friction in it. I just want to remind myself, we want to find the maximum speed of the truck if the crate is not to slide. That means we're going to max out the static frictional force. In general, the static frictional force is less than or equal to the coefficient of static friction times the normal force, but in this particular case we're maxing that out, and so we'll have the static frictional force equal to mu sub s times n. So we're going to do that. One other thing I want to remind myself of is that for an object traveling in a circle, the acceleration is going to have a magnitude of v squared over r, the radius of curvature of the path, and it's v that we happen to be after here. So those are some things that we want to remind ourselves of. All right, now the next thing I want to do, I've got Newton's second law in vector form here. I want to select a coordinate system that will make it easy to solve this problem. And so I'll just draw that right here. I'm going to let x point toward the center of the circle and y just point up. And if you're not happy with having x point to the left because you're used to it pointing to the right, walk around in front of the pickup and imagine viewing it from that direction, and then X will point to the right. But it really doesn't matter. As long as you have a right angle between X and Y, we're good to go. So, writing each force in terms of the coordinate system I've got. The normal force is just pointing in the positive Y direction, so it's going to be N in the J hat direction. The weight is in the opposite direction. mg is going to be minus mg in the J hat direction. The static frictional force, F sub s, well, it points in the positive X direction, so it's just going to be its magnitude in the I hat direction, but its magnitude happens to be mu sub s times n, and so that'll just be mu sub s times n in the I hat direction. Now remember, when I just write n like that, I'm talking about the magnitude of the normal force, not its direction. So that's what this means. Okay, well, what I usually do on these is say, okay, well, the sum of the forces in the Y direction is going to be 0. Okay, because the crate of eggs does not leap off the bed of the pickup truck in the upward direction, and it doesn't fall through the pickup truck, and so those forces must balance out. And if I just pick these off up here, I've got N in the positive J hat direction minus mg in the J hat direction, so N minus mg is equal to 0, or the normal force is just equal to mg. Now, the sum of the forces in the X direction will equal, that's the direction of the acceleration, that will equal ma. And the only force I have in the X direction is that static frictional force. So F sub s will equal ma. Now I can do my substitutions. The static frictional force is equal to mu sub s times n, but n is equal to mg, and so I'll do this in 2 steps. F sub s, which is equal to mu sub s times n, is equal to mu sub s mg, and that will equal ma, but a is v squared over r. So mv squared over r. And if I just look at this part of the equation, I can divide out the m's. I'll have mu sub sg is v squared over r. V squared is going to equal mu sub srg. And v equals the square root of that. So now I just plug in the numbers. Unit-wise, when I look at this, I have, let's see, inside meters times meters per second squared. That gives me meters squared per second squared. When I take the square root of that, I'll just have meters per second, which is good. I'm talking about a speed here. So let's calculate that. I get 14 meters per second. I can't claim 3 significant figures because I have only 2 significant figures on the coefficient of friction. So I'll just stop at 2 and pretend you didn't see that decimal point there, although it doesn't hurt. But anyway, 14 meters per second. In terms of miles per hour, that would be about 32 miles per hour. So you don't want to go too fast around this corner, or you'll have a nice mess on the ground. Okay, our first one. Now, how did I do this? Started off with a sketch, give myself an idea of what's going on here. Next thing, I made a free body diagram. looking at it from behind the bed of the pickup truck. So the frictional force, which is what produces the acceleration, points toward the middle. And then I followed the procedure like I usually do. Newton's second law in vector form, generic form here. And then for this particular problem, I selected a coordinate system, wrote each of the forces in terms of that coordinate system. I guess I didn't actually write the acceleration in terms of that coordinate system. That would look like this. ma equals ma in the I hat direction. And then in the coordinate direction where there was no acceleration, the sum of the forces must add to 0, so n minus mg. And then I proceeded through to solve it. And this is pretty much the procedure I follow on all of the Newton's second law problems that I solve. So I continued with that pattern here.